Okay, welcome to the Science Library and welcome to another Physics Tuesday with sausages, physics and potato salad. Today, the Physics Tuesday will be about machine learning and artificial intelligence. And we're going to hear about this from high-energy physicist James Catmore from the Department of Physics here at the University of Oslo. James is searching for subatomic particles and processes that are not described by the standard model of particle physics. So, machine learning and artificial intelligence might not be topics that instantly classify themselves within the field of physics, but I believe that most physicists have, at least I have, been fascinated by the idea of creating an artificial intelligence. And now it also seems that machine learning is actually sneaking in as a crucial tool to study nature, and thus becomes an important tool in fields such as physics. So we'll hear about the spectacular aspects of machine learning, but also about how it can be useful for fundamental sciences like physics. So please give a warm welcome to James Catmore.
Okay, so thank you very much for the warm welcome, and thank you for the invitation. So when people hear about... how do I move this on, by the way? There we go, awesome. So when people hear the word artificial intelligence, the image that may come to their mind is possibly this. Something extremely scary, out of control, something that's grown beyond the human capacity to control it, and something that's dangerous. If you watch too much British television, you might think of this sort of thing, which is perhaps a little less scary when they get to a staircase. But the image I want you to think about in terms of artificial intelligence should look more like this. I'm not deliberately giving a plug for the Swiss industry here, but this is the best example. Essentially, this is something that is useful, something that's adaptable, something that can solve many different problems. It's something that has a relatively simple concept. You're not going to hear anything today which is mind-blowingly complicated. The concepts behind this are actually deceptively simple. It's something that should be very easy to use and is very easy to use, but something that is actually quite hard to build, hard to make it actually work in a rigorous and robust way. It's definitely not magic, it just uses the normal rules of statistics, and it's something that you use every day. If you use Google, then you use artificial intelligence. Now, I'm not a computer scientist, I'm a physicist, and I am well aware that artificial intelligence and machine learning are not the same thing. I see that machine learning is something within the wider field of artificial intelligence. But it is machine learning that in the past few years, the past decade, has made spectacular improvements and has led to some very significant applications, both in industrial applications and also in research. So what do I mean by machine learning? I mean that it's something that uses statistical inference to extract generalities from training data. What does that actually mean? It means it's a computer program that is capable of learning from data which is fed to it. And it means, crucially, that when this thing is exposed to new data after it has been trained, it demonstrates behaviors that have not been explicitly programmed by an external programmer. It acquires these behaviors as it processes the training data. So this requires essentially two things. It requires enormous amounts of computing power, which these days we have, and it requires huge amounts of training data, whichever field of endeavor you're in, huge amounts of training data is something which is readily available. If you have these two things, then you can have machine learning doing some fairly spectacular things. I'm not going to discuss things like general artificial intelligence. I'm going to stick with machine learning, but I think this is the area in which there has been most progress in the past few years. So there are three kinds of learning, essentially. The first is supervised learning, where you give the algorithm what you call labeled data. You tell it what it's looking at, and then you ask it to identify new cases. So this can be sort of summarized by this kind of image. It's where the program is being taught what it's actually looking at. The second kind of learning is called unsupervised learning, where you don't actually label the data, you don't tell the software what it's looking at, you just let it look and find patterns within the data by itself. The third kind of learning is called reinforcement learning. This is where the program isn't specifically given labeled data, but it is given some form of score, and it can see that if it takes certain actions, the score goes up, and if it takes other actions, the score goes down, and therefore it must modify its behavior in order to maximize the score. So here you see the child has learnt that it's not a great idea to suck lemons, and therefore the score has probably gone down, so he or she won't do that again. So let's just show you the difference now between what I mean by a standard computer program and machine learning. Let's imagine that you want to write a program that can identify different letters in handwriting or something like this. So the letters are described by this 8x8 grid, and you can see this clearly makes the pattern of a letter A. You can look at this immediately. So you might think, how do I write a program that can recognize this as an A? So it might go something like this. You say, well, if the first square doesn't have anything in it, and all these don't have anything in it, but this square at position 3, 4 is red, and the one at 3, 5 is red, blah, 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 blah. If all of these squares that are here are red, then it's an A. Otherwise, it must be something else. So that you think, well, I've done my job, perfect. And then you get the next day, and unfortunately, it's in the corner of the box. And then you see that this program immediately doesn't work, because here there's nothing, and then here you've got 2 red squares. So, okay, the program's not very good. So you think, okay, well, I can put a big OR statement here, and then say, or, if these 2 are blank, and there's a red one here and a red one there, etc., etc. And then the next one come along, and they look like this. And very quickly you realize that this approach is not going to work. This is where machine learning starts to become useful. Because what you do with a machine learning algorithm is you essentially present it with lots and lots of cases with a given label. So you say to it, this thing, represented by these squares being red, is called A. This thing is also called A, and so is this, and all of these are as well. It doesn't matter that it's an A. You could call it anything. You could call it elephant or banana. You've just given it a label. And then you can do the same with the other letters of the alphabet. You can say this is a C, and this is an E, and this is a V, and then give it tens of thousands, hundreds of thousands, millions of additional cases. And they all get fed into this algorithm. And then what you can do is you can give it a new case. You can say, what does this look like? And in the course of the training, what has happened is an internal state of this algorithm has been developed. A large number of values have been acquired which associate what you have given it, what you have shown it already, with the labels that you have provided it with. And then having looked at the new information and made a comparison with its training information, what you get out is a probability and a result. And in fact, the probability, at least as far as what we're doing in high-energy physics is concerned, is far more interesting than the actual result. So you can see here, I've just made this up, but you could imagine it would give a percentage of 78% probability for it being a V, or it could be a U, 20%, or it could be a C, or it could be an L, conceivably. So the final decision is V, but actually it's the probability that's more interesting. So you've been given a probability based on everything else that it's seen that this is a V. And of course, the more information you provide it, the more training data you provide it. In principle, if the training data is good, then these scores should improve. With the unsupervised learning, you don't actually provide any labels. You just throw in all of the information, tens of thousands or millions of these cases, and then the algorithm essentially tells you, well, these things, I don't know what they are, but they look very similar. I don't know what these are either, but they also look similar, etc. This is called clustering, and this is one example of unsupervised learning, where you don't actually give the thing any labels. Now, what's actually going on under here? I promise this will be the only equation that I write. What's happening behind the scenes is something called the minimization of a cost function. And what this is essentially expressing is how far am I away from the target values that I'm trying to get at. So this thing called the cost function, basically it has all of these parameters. And these parameters are all these numbers, the internal state of the algorithm. And you have this expression. And what this is saying is, what is the sum of the squared difference between the prediction of the model when the training data is given to it and the target? In other words, how far away is it from the right answer? In the case of the supervised learning, this is obvious. How far away is it from the label that you've given it? or in the case of the unsupervised learning, there's some metric how far these different clusters are away from each other. But essentially what happens then is that during the training procedure, it varies all of these parameters. There could be 2 parameters if it's a simple straight line fit, or there could be millions of parameters if it's a big neural network. But essentially what it then does is it does this minimization using something called the method of steepest descent or gradient descent. And it's minimizing these parameters, and you end up with this multidimensional surface. It's just shown with 2 dimensions here. But this is these parameters. And it's trying to find the minimum position. And the minimum value, or a minimum value, should represent the value of all these parameters which best matches the training data that you've given it. Now, I said this very glibly. Actually, this part is the hardest part of the machine learning. This minimization is extremely complicated to make it actually work properly. To deal with things like local minima, to deal with noise, etc. This is where really the hard work of machine learning is. And I believe this is a lot of where the pure research is taking place, how to make this thing work effectively, but also quickly, because if it's not done properly, this can run very, very slowly, and then the algorithm is essentially useless. So that's what's going on behind the scenes. This is something I was running this morning. You can see here, this is the loss function, and you can see that with each cycle of training, the loss function is getting lower and lower. In other words, it's getting closer and closer to the training data. Now, there are all kinds of machine learning algorithms, and this is what's called a cheat sheet. This is from Microsoft, but there are many other similar ones where they're showing all the different kinds of algorithm, whether it's trying to classify multiple classes or just 2 classes, whether it's doing clustering or anomaly detection, trying to see things that are different from things that it's already been seen, or regression. But in the end, many of the underlying features are quite similar. I want to focus on one particular class of machine learning algorithm today. That's the neural network. So this is essentially something that's based on how we currently think the brain itself is working. This is a beautiful image by somebody actually within our area. This is from Milad from Sinpla, who did this beautiful rendering of a neuron cell. The structure of it is extremely complicated, but you can break it down into fairly simple parts. You have the dendrites, which act as the input. You have the nucleus here. You have this axon, which is this long tail, and then you have the axon terminals, where there is an output. We don't know exactly what's going on in here, but there are people in this university and in many other universities around the world trying to figure out exactly what happens in these neuron cells. But in computer science, a much simpler version of this has been put together, and this is called a perceptron. So what we have here, we have a number of inputs. We have weights, which are essentially you multiply by the inputs, and then you have a sum, so you take a weighted sum of the inputs. You then have some function called an activation function, which does something with this weighted sum, and then you have an output. So this is a very simplistic model, essentially, of what a neuron cell might be doing. But what the magic happens when you start linking lots of these perceptrons together into what's called an artificial neural network. Each of these is a single unit, but you can see there are lots of weights linked to the next layer, and then you can have several layers or many layers. And as you follow, these weights become increasingly entangled, and you can model some very complex nonlinear behavior using these things, which is why neural networks are so powerful. If there's only one, what's called hidden layer, then the network is regarded as being a shallow network. If you have more than one, so for instance, in this case, you have 2 or 3 hidden layers, the network is called deep. And the way these things are trained is you provide some when you're training the thing, you provide it with some output information to match to the input data, and then you do something called backpropagation, where you update all of these weights simultaneously in order to minimize this cost function that I showed on the previous slide. And you can imagine with all of these weights, this rapidly becomes very complicated. But the power of these things is that they can model very complicated nonlinear behavior. So the thing that I showed you on the previous slide was called a fully connected neural network, and they are themselves very powerful. But if you make certain assumptions about what the neural network is expected to do, for instance, recognize images, you can start making alterations to the structure to fine-tune this. So, for instance, there's something called a convolutional neural network that assumes that it is looking at images, and the design is assuming that it's for classifying images. There's something called a recurrent neural network, which is specifically designed to look at time-dependent sequences. In this case, it may be useful for recognizing speech or comprehension of text. And when it comes to the convolutional neural networks, or in fact a combination sometimes of the convolutional and other kinds of neural network, you can make pretty spectacular achievements with this. For instance, when shown this image, this particular neural network was able to give the following phrase: person rides elephant past shop. Now, I find that, when I look at that, I find that pretty freakish. But this is what this thing is able to do. It has been trained on a colossal amount of data to enable it to do this. But this is the kind of thing it can do. And with these convolutional neural networks, what you're looking at here is the ability of these algorithms to correctly classify various images, not giving a phrase in this case, but just giving a one-word description. And you can see over time, the accuracy of these things has improved to the extent that now these things are about as good as a human being at recognizing images that they are shown, which is clearly extraordinary. Now, once you've got to the ability to recognize objects with this kind of precision, it doesn't take a huge amount of imagination to get ourselves into this kind of position. I suggest, if you haven't looked at this video, you look at it. This is provided by Tesla. I am using Tesla as the example here because they've produced more information that they've made public, but many other manufacturers of vehicles are doing this. I don't hold shares in Tesla. But what you see here is in this video is a car which is really driving itself. And it's quite spectacular to see it on normal roads, through cities, through towns, etc. And what makes it interesting, or doubly interesting, is that you can see what the machine learning technology is actually doing as the thing is driving in real time. So it gives color code. So, for instance, it's able to recognize the road markings to guide the vehicle into the right place. It's able to recognize objects which are in its current trajectory that it needs not to crash into. It's able to recognize objects that are not currently in its trajectory, but which may be at some point. It's able to see road signs. And then, you see really quite spectacular things such as this. It's able to see things, for instance, a cyclist who passes on the inside, which is something a cyclist shouldn't do, but anyway, this person did. And you can see that the thing has, initially, it saw that there was an object that could be potentially in its path, and then as he got close and got alongside the vehicle, it recognizes this fact. Now, of course, the cameras are facing in all directions. A human driver can only look in one particular direction. So you can imagine very quickly that with cameras pointing in all directions, where all of these images are being processed simultaneously, this becomes very, very powerful. And of course, the thing isn't just looking at images with cameras. It's also using ultrasonics, it's using radar, etc. And more than this, it also has the ability to learn from what other vehicles are doing. They're all connected together, and it therefore improves its skills at recognizing objects as time goes on. So this is really something that's worth looking at if you haven't seen it already. Now, another area which people got extremely excited about a few months ago was where this company called DeepMind, which is based in London, played this game Go, which is a game played in East Asia. And it was previously thought more or less impossible that a machine would ever be able to beat a human player. I'll say why in the next slide. But the long and short of it is that the computer, or the program, the machine learning program AlphaGo, beat the world champion by 4 games to 1. So, of course, I was a bit torn here. I was kind of hoping the human being would win, but then the program was playing under the British flag, so I was a bit conflicted here. But the reason that this was considered to be more or less impossible, if you take chess, on average there are about 35 moves that a chess player can take for any given position. In an average game, there are thought to be around 80 moves in total in a sort of average game of chess. The total number of combinations, therefore, is 35 to the power of 80. Now, if you take Go with the sort of standard board, you've got 250 moves per position raised to the power of 150. So the total number of combinations is basically incalculable. Even for one move, it's more or less impossible, and two moves. So the traditional chess-playing computer programs, which essentially use brute computational force, were just completely hopeless at playing Go. But what the DeepMind company did is they, first of all, trained a deep neural network, or a series of deep neural networks, first of all to learn from the moves played by human beings, to look at what moves people took for a given position of the board. And having done this, having trained it on many games which it learnt online from human players, it was then set to play against itself, and this is where this reinforcement learning comes in, because it was trying to maximize a score by taking these actions based on what it's already learned. And then finally, something called a tree search, which is, I believe, how chess games are currently played, or something like it, was then combined with these neural networks, and this enabled it to have this kind of behavior. And it was very interesting to read the reports that people had written. They said that the machine adapted a very unusual playing style, very conservative with the words that were used about the thing that this adapted, just from having learnt from human beings and playing against itself. There was an argument, actually, that this was a victory still for the human being, because the human being, the human being's energy consumption was a few lunches, whereas the computer had consumed megawatts of power. But even still, this is a clear victory for the machine learning algorithm. Now I'm going to come to my own area to say something about the physical sciences. So I'm in the particle physics group. This is our beautiful accelerator, the Large Hadron Collider, which is colliding beams of protons at 13 trillion electron volts. They're being collided at 4 places around the ring, underground. This is one of the 4 detectors. I'm not showing it at random. This is the Atlas detector, which is the experiment that Oslo is involved with. You can see the size of it from these people represented here. The beams of particles smash together in the center. They produce a spray of particles. And this thing is basically a gigantic digital camera, a 3D digital camera that can see charged particles and can detect the energy deposited by particles, as well as just photons, which is what your digital camera sees. And it rebuilds images that look something like this. There are around 700 per second of these things coming out of the... there are far more than this, but we're recording something of this order. And you can see here the trajectories left by the particles, and then you can see them being built here into higher level objects, things that we call jets, muons, electrons, etc. And from this information, we then perform what's called physics analysis, where we try to figure out what has actually happened in these collisions. Now, if you look at these images, and then you look at these images, to a computer or to a machine learning algorithm, there may not be a great deal of difference between the two. So one of the things that we are looking at in our collaboration at the moment is whether we can use exactly the same kind of image recognition and trajectory analysis which is being used for the self-driving vehicles, whether they can be used and applied in the reconstruction of particles and objects in the detectors. Now, moving a bit further downstream to what physics analysts are actually doing, some people who are sitting in this room working on this kind of thing, we end up with what's called signal and what's called background. And in general, we don't really, if we're using simulation, we know which is signal and background, but if we're using data, we don't know which is which. So we have to try to chop out as much of the background as possible whilst keeping as much as possible of the signal. I've shown this here quite simply for 2 variables. Of course, we can be dealing with many more variables. But here what we do is we make things called rectangular cuts, where we just chop off around where we think the signal is. And you can see an immediate weakness for this because we've got some contamination here from these blue dots. Now, if we use something called multivariate analysis, which is basically what particle physicists call machine learning, you can define some kind of boundary that's far more adaptive and that can fit the data far more precisely and therefore get a much better view of what we're actually trying to separate out. And of course, as I said, this is just in 2 variables. In reality, we can have many more variables than this. That's why we call it multivariate analysis. Now, no talk on machine learning is complete without seeing this thing, which is called a response operator curve. And what this is basically showing is how good is this algorithm at separating the background from the signal. You see here we've got the background rejection, the percentage of background rejected, and the percentage of signal accepted. A perfect machine learning classifier would have a plot that looks something like this. In other words, it rejects all of the background and accepts all of the signal. If it's doing no better than random, what you get is a diagonal line like this, where it has a 50-50 chance of being on either side, and it's just doing, you could just guess and you wouldn't do any better. And if it's somewhere between, the curve looks like the green line. Now, what we have in particle physics are two kinds of variable. We have low-level variables, which is basically the information that has been directly recorded by the detector, things like the momentum of the particles, how much energy they deposited into the detector, etc. We have something called high-level variables, and these are things that we calculate from the low-level variables using our knowledge of physics. So, for instance, we can apply the laws of energy and momentum conservation in order to calculate additional variables. And this is traditionally the kind of variable that we would be putting into these plots. They would be high-level variables that we have calculated from the low-level variables. And the question is, does an artificial intelligence agent do better if it has been presented with only the low-level variables, only the high-level variables, or both? And that's another way of saying, can the artificial intelligence learn physics all by itself? And it seems from very early studies that have been done that the answer is actually yes. What this is, these curves that I was talking about before, this is where you only provide it with the high-level information. This is the red curve. The blue curve is where you give it both the low and the high-level information. So this is the sort of thing that a physicist would give it. And then if you only give it the low-level information, you see that it's not really done any better or not done any worse. Meaning that essentially, in this particular case, the low-level variables, the high-level variables, the application of the laws of physics from outside hasn't really helped the algorithm. It's managed to learn all this by itself. This is potentially very powerful. It's in its very early days, and we're not sure if we're kidding ourselves here, but this is looking like it's something that may become very interesting in the future. So I'm going to finish off now by saying something on general intelligence. So this is basically what we are. We are generally intelligent. We're capable of doing all of these different, well, most of us, hopefully. We're capable of doing these, all of these activities in the same brain, and we're able to play chess 1 minute and then work out how to make dinner the next minute, etc. Whereas all of the things that I've talked about so far are what we call narrow intelligence. The neural networks for driving a Tesla or for playing Go are excellent at doing those jobs, but if you ask the Go algorithm to drive the self-driving car, I suspect that the Tesla would be very quickly driven into a tree. Similarly with image recognition software. So this is the big difference. And as far as I'm aware, not much progress has been made in developing general artificial intelligences. And I think possibly one of the reasons for this is a question of energy. So what we're seeing here is a plot that shows the computing density, in other words, the operations per second per liter, per volume of material, plotted against the computing efficiency, in other words, the operations per unit of energy input. And you can see that there's been roughly a linear, well, this is a logarithmic scale, of course, an exponential improvement as time has gone on. But you can see this is the IBM Roadrunner from 2008. Other machines have actually been built since then, but they're kind of starting to plateau off, and they're not carrying on along this line. But you can see how far they've got to go. You've got human beings and whales and elephants and so on, which are at least 4 orders, maybe even 5 orders of magnitude away from where the best biological brains are. And this is really starting to tail off. So I think we may be starting to see the limits of what silicon technology can actually do here. But, of course, silicon may not be the end of the story. There are things already being built which are actually still silicon, called neuromorphic circuits, where you don't have a standard kind of Intel layout, but you have a specially designed layout which assumes that you're going to be doing deep learning, and also using things like graphics cards. But then you can get to things like non-silicon semiconductors, gallium and things like this, which may be able to perform more quickly and more energy efficiently. There's the possibility of optical computing, where instead of electronics, you're using optical elements to do some of the processing. The possibility of merging biological tissue that may have been somehow produced in a laboratory with electronic circuitry, maybe this is a way forward. And finally, this is way out, and I really don't know very much about it, but possibly even the chance that we could use quantum computers. So whilst I don't think we need to worry yet about computers reaching the levels of intelligence with silicon technology, I wouldn't like to say what's going to happen in the future with all these other possible technologies. But this is extremely futuristic, and none of this is beyond its very early infancy at the moment. I'm going to finish off now with some discussion about public concerns, and I'm not really going to go through this because, I'm not a social scientist. So, I mean, these are the sort of things that you read about in the media every day, the kind of concerns that people have. Whether artificial intelligence is going to represent a threat to employment, whether it will strengthen capital at the expense of labor, whether there are certain pernicious effects of these recommendation systems, in other words, bubbles and fake news and this kind of thing appearing on people's Facebook feeds. There's a worry that people are handing too much control to artificial intelligence systems that might not be fully understood. So, for instance, are we giving financial trading systems too much power to make a complete mess of the financial markets? Although the people seem to be able to make a mess as well. So, or self-driving cars, for instance, what happens when one has a collision? Does it also cause human beings to lose their own expertise? And I think the best way of demonstrating this, if you can imagine that you've been using your self-driving car for 8 months, you've never had to take control, and then one day you're going along the motorway at 70 miles per hour, and suddenly an alarm goes off that says, take control. I think most people would just go into a blind panic and wouldn't know what to do. So that's another element of concern. I'm going to leave this perhaps for discussion later because this isn't an area of my expertise. So I think that more or less summarizes what I want to say, and I guess there may be some questions and comments afterwards. So thank you very much.
Thank you, Alia. Yeah. Thank you. So you may just raise your hand if you have a question to the speaker. No, really? There's a question. Okay.
Can you go back to the cost function, please?
The one equation.
Yes. Am I wrong when I'm saying that is very similar to a variance calculation?
Yes. Very similar. Yep.
Yeah. So
yep.
I'm right. Yeah.
Yep.
So you're actually doing some sort of least squares thing, or?
Well, this is essentially what's happening.
Yeah, yeah.
And this isn't the only kind of cost function. There are others that can also be used, but this is typically given as an example, and it's what's used, I believe, in many of these algorithms. Yeah.
Okay. Thank you.
Hello, thank you for a very interesting talk. I have a question about using machine learning for physics, because how do you know that your model, or do you use hand-labeled data when doing machine learning on these data sets, and if not, how do you know that you're not just getting sort of the same assumptions out of the model?
Rubbish in, rubbish out, in other words. Yes,
yeah.
This is the main problem with using these algorithms, and it's, in our collaboration, this is not a settled question, and it's not a settled question in our field, I think, because you do rely on Monte Carlo, on simulation, in order to train these classifiers. So you have to be very, very sure that what you're training it that it isn't, for instance, just learning elements of the simulation, which of course have just been fed in, and that it is actually learning something real. So there are a variety of ways in which you can mitigate this. You can, for instance, try to define control regions in the data where you're certain that there isn't contamination from signal, but which still is actually data that you're training it on. And the other thing we have to do is set systematic errors. We have to try to figure out how good or bad, by testing against control samples, for instance, the Monte Carlo actually is describing the data. And then we have to try to propagate these uncertainties into whatever comes out of the final answer. And with machine learning algorithms, this is much, much more difficult than it is using this what we call rectangular cuts. And this accounting for systematic uncertainties is actually one of the main stumbling blocks that this sort of thing, this technology actually has in our field. So you've put your finger essentially on the main problem with using these technologies.
Thanks.
Hi. Thank you for the talk. What do you think is the next big breakthrough in terms of artificial intelligence or artificial general intelligence? And in which industry and maybe some of the impacts?
If there's a computer scientist in the room, this would be a great time for that person or people to speak up, because I don't know. I mean, we, as a physicist, things have advanced so much in the past few years that we are kind of jumping onto this, we find many of these things already amazing that are capable of being done. I mean, I don't know. I would think that this is the kind of area where, there are many algorithms being developed, and they have extreme power. Companies like Google and so on are putting massive resources into this. But I see this as being the main limitation. The fact that in the end we're limited by the efficiency in terms of energy and volume of our current computing technology. So I think the next massive breakthrough will be when something like this can come out. But I don't know. If there are computer scientists who want to comment on this, then this would be a great time to do so.
Hi, thanks again. How steep would you say is the learning curve for new users?
Not very steep at all, actually.
Does that mean that YouTube can do it?
If you know, I mean, for instance, you need to know some basic programming in order to set the thing up, because, so it helps, for instance, if you can, most of the tools that we're using at the moment, for instance, are Python-driven. And it definitely is important that you have some knowledge of linear algebra so that you can kind of work out that your data structures are correctly set up and so on. But if you are basically, numerate, if you're able to do these things, then yeah, for any undergraduate in the physical sciences or in mathematics or biological sciences who've had some contact with basic linear algebra and basic programming, I would say the learning curve is not so much at all. And also with some of these Python-driven tools, TensorFlow and scikit-learn and so on, the documentation is really fantastic. They are not words that you often hear, certainly in our area of research, put together, but the documentation is really excellent. So I think this is, I think with some caveats, it is something that many people can try to learn.
Thank you for the interesting talk. And I have a question. Maybe it's similar as the previous question, but maybe it's extended to a special case. So you mentioned the low-level variables and high-level variables, which is calculated from the low-level variables. Yep. So in physics, when you do the calculation, and for example, the first principle calculations, you have some assumptions you need to make. Yep. To assume some parameters are fixed, and then you can. So how the machine learning can learn that assumptions are valid?
Well, because, we're not quite sure. That one of the problems is it's quite hard to figure out what these things are actually doing, because you have these many nonlinear combinations. But, if you look at millions and millions of particle events, for instance, the algorithm may quite quickly learn that in most cases the energy is balanced, the momentum is balanced across the different parts. It isn't always, of course, because sometimes you might get neutrinos being emitted which aren't detected. But in general, it will start to observe that when a particle decays, it decays in a certain way, and it doesn't necessarily need to have the assumptions that we make put into it, because it can see it. It's observing millions and millions of events. So it kind of gathers what's going on just by looking at it. Another point is it may also be learning things that we haven't thought of. It may be learning properties that we haven't considered, which may or may not have meaning. But I think it's just because it's looking at so many events, in this case at least, that it's actually able to uncover underlying physical laws.
Thank you.
Thank you for a great talk. Do you think artificial intelligence will give us eternal life?
I don't really feel qualified to answer that question, to be honest. Well, I guess what you're saying is, would it ever be possible to download the contents of a human brain to an AI system that would then mean it became independent of the body that was sort of gradually, decaying or whatever? And I think we then come back to this plot again. I don't think that will be possible until we are able to make computational technology which has the same energy efficiency and volume efficiency as a human brain. And as I said, this isn't possible with silicon. Now, who knows what will happen when we're able to grow large numbers of artificial neurons and connect them together. But with current technology, I think this is probably impossible.
Hello. So what benefits do you think you would see specifically for your project in the future?
Right, yes. Well, what I hope is that we will be able to spend less time, for instance, let's give an example. We have something called data quality at the moment, where we have to worry whether our data is properly, whether the data from a certain run of the LHC is consistent and is valid, or whether something has gone wrong with the detector. And we spend hundreds of hours of person time worrying about this kind of thing, trying to detect problems. If we can develop algorithms that are able to kind of flag this sort of thing automatically, to take some of this kind of labor away, if we're able to have fewer people doing shifts, monitoring data, monitoring the behavior of the detector, this would already be a massive improvement. And this has nothing to do with physics analysis. This is just taking away some of the sort of donkey work that we have to do in order to keep our systems running. In terms of physics analysis, at the moment we have to assume what our data and what our signals look like. I kind of have some dream eventually that we may be able to do a similar kind of thing, where we don't actually show the artificially intelligent program what the new physics is supposed to look like, that it will be able to find it itself just on the basis of the training using standard model, in other words, known data. Then we come back to the previous speaker. It's very difficult to train something using Monte Carlo without kidding yourself. So that's another area. And I think the third area is this kind of thing, where we can maybe spend a little less time writing software for reconstructing events in physics. Maybe we can make more use of graphics processors by using deep networks to build these objects, rather than having to write procedural software for doing this kind of reconstruction. So I think these are the three areas which we really hope for improvements. And it's not about replacing physicists, it's about giving physicists more time to do physics rather than doing the many other things that we currently have to do.
Okay.
Yeah, so this is the last question.
Okay, thank you for a very good introduction to this topic. My question is actually a follow-up of what other people have talked about here. When we have had this algorithm learned and adapted to this data set, are we actually able to learn something from the artificial learned intelligence? Or are we able to learn from the patterns?
Yeah. That's something that the people who are working on this kind of thing are looking into. Are we able to glean new information from how the algorithm itself, rather than just using the algorithm to do the task that we've asked it, Are we able to look at what the algorithm has learnt? Are we able to look inside the various weights? This becomes extremely challenging with these deep networks just because there are so many weights in there, millions and millions potentially. But if we were able somehow, by various clever techniques, to look at what the thing has actually learned, maybe we can give ourselves new perspectives on how we can actually do the physics. And this is one of the ideas in this kind of area.
Okay, thank you very much for your
My pleasure.
fantastic, I would say, presentation. So here's a gift from Biblioteket.
That's very kind. Thank you very much indeed.
So the next Physics Tuesday comes in just 2 weeks, and it will be about the RF cavity thruster, or more commonly known, the EM drive, where Alexander Bribricker from Andøya Space Center will talk about partly about science and how people perceive science, because one of the really interesting aspects of the EM drive is how the media reacted, were sort of polarized to the news about the EM drive. But ultimately, he will also try to answer the big question about EM drive, which is whether it actually works. So we hope to see you back here in 2 weeks. Thank you.
Thank you very much. Thank you.